Professors, associate professors, doctors, candidates, colleagues and friends of academics, electronic navigation, and naval operations. My name is Bård Eriksen, Commander of the Royal Norwegian Naval Academy. On behalf of the Chief of the Navy, Admiral Stensønes, and the Superintendent of the Norwegian Defence University College, Admiral Dedican, I welcome you to the Royal Norwegian Naval Academy. This is a great day for us in many ways. It is a disputation on a highly relevant topic. We emphasize the link between academics and naval operations. We also strengthen the network of the maritime domain, naval operations and different universities. The Norwegian University of Science and Technology, the University of Tromsø, the Western Norway University of Applied Science, Gdynia Maritime University, and the Norwegian Defence University College. We are all really looking forward to this day, so welcome to all of you. And by these words, I would like to give the word to the chairman of the committee, Professor Hildre.
Welcome. On behalf of the National Joint PhD Program in Nautical Operations, the Norwegian University of Science and Technology, and the Royal Norwegian Naval Academy, it's a great pleasure for me to welcome you all to this trial lecture on the assigned topic held by Sveinung Hareide. The use of eye tracking technology in marine high-speed craft navigation. That was the submitted thesis on the 9th of September 2018. The following committee was appointed: Professor Adam Weintritt from Gdynia Maritime University in Poland, Department of Navigation, as first opponent, and Professor Margareta Holtensdotter Lutzhoft, Department of Marine Studies, Western Norwegian University of Applied Science, as the second opponent. And me, Professor Hans-Petter Hildre, Department of Ocean Operation and Civil Engineering at the Norwegian University of Science and Technology, and I'm the head of the evaluation committee. A trial lecture on the assigned topic is a requirement for the degree of philosophy doctor at the Norwegian University of Science and Technology. The committee has already found the submitted thesis of Mr. Hareide worthy of being defended for the degree of philosophy doctor. However, a trial lecture must be achieved the grade passed before the candidate is allowed to public defense of the submitted thesis. The committee has decided that they will interrupt the candidate only for the clarification during his presentation and ask questions afterwards. Also, the audience may ask questions after the presentation just to feed your curiosity if it is anything you want to know more about. 2 weeks ago, and according to the regulation for the philosophy doctor degree, Mr. Hareide was given the following topic for his trial lecture. It was there for a minute ago. S-mode as one of the important milestones on the way to the full implementation of the navigation concept. The trial lecture will last for exactly 45 minutes. I now ask Mr. Hareide to give his trial lecture on the assigned topic. Mr. Hareide, please, the floor is yours.
Thank you, Professor. Okay, thank you. We are also on a live stream. Does it work, Håkon? It's okay? Distinguished committee members, supervisors, vice dean, commander, colleagues, dear family and friends. Welcome to this trial lecture on the topic of S-mode as one of the important milestones on the way to the full implementation of the e-navigation concept. I will start by outlining the e-navigation concept and further elaborate on S-mode and how this can be seen as one of the milestones in the further implementation in the e-navigation concept. As shipping moves into the digital world, e-navigation is expected to provide digital information and infrastructure for the benefit of the maritime safety, security, and protection of the marine environment, reducing the administrative burden and increasing the efficiency of maritime trade and transport. The formal definition of e-navigation was adopted in 2008. E-navigation is the harmonized collection, integration, exchange, presentation, and analysis of maritime information, both on board and ashore by electronic means, to enhance berth-to-berth navigation and related services, for safety and security at sea and protection of the marine environment, unquote. The need for e-navigation is embedded in the IMO's e-navigation strategy plan for the development and implementation of e-navigation. The aim of e-navigation is to meet present and future needs through the harmonization of marine navigation systems and supporting services. The overall goal is to improve safety of navigation and to reduce errors by equipping users on ship and ashore with modern, proven tools optimized for good decision-making to make maritime navigation and communication more reliable and user-friendly. E-navigation developments in communication and information technology provides opportunities to develop knowledge management so as to increase transparency and accessibility to information. E does not mean electronic, rather enhanced or evolved. Some also argue for I navigation for integrated or improved. In 2016, the Secretary General of the International Maritime Organization, Mr. Ki-Tak Lim, delivered the keynote speech to the conference E-navigation underway, and I quote, "E-navigation is the future, but it has been the future for a long time." He further explains his statement with, "The challenge now is to turn the future into the present, so that the all much heralded benefits and advantages of e-navigation can be fully realized." The e-navigation development process involves many stakeholders, such as ship-borne users and shore-based users, including IMO member states as flag state, coastal states, and port states, international organizations, industrial actors, research institutes, service providers, and others. E-navigation has a clear aim to strengthen the safety of navigation, to increase the efficiency within maritime transportation, to further develop a global, sustainable maritime transport system, which all supports the United Nations Sustainable Development Goals, the SDGs, which is highlighted by goal number 13, and goal number 14, which is the use of the ocean, seas, and marine resources. This is to be done by utilizing digitalization within the maritime to create simpler, smarter, and more efficient communication, both ship-to-ship and ship-to-shore, simplify the administrative work both on board and on shore, such as the Safe Seanet to reduce the amount of forms. Thirdly, to increase efficiency or save time by making access to digital information, such as weather information and seamless updates of electronic navigation charts. And fourthly, to increase the user-friendliness and knowledge of maritime equipment and systems, such as the S-mode, which I will come back to. And finally, of course, to support safe navigation and the navigations team situation awareness. The use of the digitalization will lead to reduced administrative burden and a risk reduction of accidents. The result of further development of the IMO strategy plan was the finalization of the e-navigation strategy implementation plan, the SIP, which is based on 5 prioritized e-navigation solutions, which actually was 28 potential solutions, but 5 is now prioritized. This plan was approved after a comprehensive process in 2014, and the SIP is mainly a guide for all stakeholders to raise awareness of the specific user needs related to e-navigation and the prioritized solution to address the user need in a cost-effective manner. The SIP was further updated in 2018. The further work with the strategy implementation plan is emphasized to be done in a harmonized and standardized manner. I would now like to highlight the 5 solutions, and solution 1 is improved, harmonized and user-friendly bridges. I will come back to the S mode, which lies within solution 1. Another example is the Open Bridge project, where the aim is to develop an open platform that provides better and safer user interfaces on ships, simplifies multi-vendor integration, and opens the ship bridge for new applications. Solution 2 is the means for standardized and automatic reporting. An example is the Safe SeaNet Norway, which is Norway's single-window portal for ship reporting, aimed to reduce the administrative burden for the bridge team. Solution 3 is improved reliability, resilience, and integrity of bridge equipment and navigation information, such as the increased focus on resilient position, navigation, and timing, PNT, which is also very important for the Norwegian Navy. One example is the use of aileron and radar positioning, or the use of signals of opportunity, such as the ranging mode, the R mode, which uses the differential GNSS broadcast as signals of opportunity. Solution 4 is integration and presentation of available information in graphical displays received via communication equipment, such as the Maritime Cloud, which is a communication framework enabling efficient, secure, reliable, and seamless electronic information exchange between all authorized maritime stakeholders across available communication systems. And solution 5 is the improved communication of vessel traffic service, the VTS, service portfolio, but it's not limited only to the VTS station. An example is the digital route service for vessels leaving and arriving Norwegian ports. The digital route service enables vessels to get access to quality-assured recommended routes and route information on current local regulations when sailing to relevant port and quays, and route distances. It is expected that these tasks, when completed, should provide the industry with harmonized information in order to start designing products and services to meet the e-navigation solution. As an example of e-navigation, I would like to explain how it is expected that e-navigation will transform passage planning, which consists of the appraisal, planning, execution, and monitoring stage. The first step, known as the appraisal stage, is to gather all relevant information for the upcoming voyage. In this regard, the navigator has to consider what information is relevant and where to find it. This takes a lot of time, as there is a huge amount of information and resources available in different books and publications. The challenge of gathering all relevant nautical information from many different sources can be complex and time-consuming. Furthermore, the navigator has to make sure that all data is up to date. Another important thing is to know how to use these resources and to understand how to interpret and apply the information the correct way. Fortunately, digitization has already started to improve the situation. And going forward, manufacturers believe that all the information will be digital and available on demand. Updates will be seamless and automatic, transforming the appraisal stage from being a manual and time-consuming task to a safer, easier, and automated procedure. Today, when starting the planning stage, the navigator will typically use a spreadsheet to manually prepare a detailed plan for the voyage. Doing it manually is also very time-consuming, as they have to fill out a lot of information such as latitude and longitude, course and speed, rate of turn, tidal data, and more for each waypoint in the route. Imagine filling this information in for, let's say, 140 waypoints. We are talking hours every day with high risks of typos that could be flagged as deficiencies by vetting or port state control. The large workload has in some instances resulted in bridge officer cutting corners, which can jeopardize safety. With automatic logging and calculations of nautical information, e-navigation technology will make the planning stage more efficient, accurate, and safer. All the required information will be filled in automatically for each waypoint, and digital safety checks ensures the safety of the vessel and the crew by analyzing the route and comparing the navigational data with the vessel's draught, height, and other specifications. In the future, manufacturers expect the planning stage to be a fully automated process. Then we come to the execution stage, and we see that today ship reporting remains a huge administrative burden for a vessel which embarks on a voyage. There are tens, sometimes hundreds of different reports a ship may be obliged to submit during a single journey, many of which mostly contains the same information. This could be solved by the concept of single window portals, which means that navigators can use one single portal to submit all their documents for port and authority clearance. The project is also looking to develop a system that will enable the machine-to-machine interaction without the need of human input. In other words, an automated ship reporting will save bridge officers valuable time. When the vessel is underway, the navigator is responsible for maintaining safety, and we now come to the monitoring stage. This could also be a challenge, as shipping is an industry full of surprises. No matter how many hours a navigator spends carefully appraising all relevant information and planning the intended voyage, there is always a chance that conditions could change. Unexpected situations could occur, for example, be sudden changes in weather, an accident, shift of cargo, sickness, injuries, or unexpected technical difficulties that demands a change in route, or that the vessel seeks out a port of refuge. With better connectivity between ship and shore, it is possible for fleet operation centers to assist the vessel if any unexpected situations occur. And in the future, there is also a great potential in using augmented reality, AR, to enhance the navigator's situation awareness by placing information from the electronic chart display and information system, the ACTIS, and other information systems directly in their field of vision. Examples of such information could include course, speed, and route information. To conclude this example, we see that the world is being digitized, and the steady advance of information and communication technology and the ever-increasing amount of data will continue to drive unprecedented change. This means that even traditional industries like shipping will go through great change. It is clear that e-navigation will transform all stages of the passage planning process and increase safety and efficiency. This will save hours of time, reduce costs, avoid accidents, and eliminate deficiencies. It could also play an important part in making shipping greener and more sustainable. S-mode means standard or standardized mode. The definition of standardization within the S-mode guideline is suggested to be, and I quote, the achievement of the optimum degree of order in the user interface provided by different equipment manufacturers for essential navigation functions and information. The optimum degree of order is that required for safe and efficient navigation and to minimize the variation and complexity of navigation equipment for the users, unquote. Large variations in the user interface of electronic equipment can significantly inhibit an operator's effectiveness in performing the navigational task. Where there is significant variations in buttons, icons, actions, workflows, processes, units of measures, or location of information, there is a commensurate increase in the time required for equipment familiarization and the risk of operational error, particularly in the challenging navigational situations. Users need to be better able to accumulate knowledge, skills, and experience of using essential functions, which can be transferred between the systems and equipment of different manufacturers. To achieve this, essential functions and information needs to be located in consistent locations, be of a similar size, recognizable by location, color, and shape. Units of measurements should also be consistent. As an example, the Maritime Accident Investigation Boards, the MIB reports, they reference more than 30 manufacturers of the electronic chart display and information system, the ACDIS, which I have 4 examples of here, all with different user interfaces. The need for familiarization and system knowledge is highlighted as one of the major contributors in several MIB reports. Vast amount of information are made available to the user of electronic navigation equipment. To a large extent, the safe navigation of a ship depends on a user's ability to identify, understand, and interpret essential information in order to perform navigational functions. Good decision-making depends on the effective and efficient use of essential information from across different pieces of equipment. Different manufacturers often produce these different pieces of equipment. The use of standardization design principles across key systems and equipment will improve design consistency, reduce the navigator's head down time, increase the situation awareness, and provide users with more time to look out, evaluate situations, and monitor a ship's safe navigation. A greater extent of standardization will reduce the time needed for familiarization, but as a contrast, it is important that the standardization does not limit the innovation degree of the manufacturers. There needs to be a balance, and as an example, a standardized user interface covering ACDIS could hamper the innovation. The S-Mode guideline was developed by first an informal correspondence group, which developed into a formal correspondence group, which consisted of a large number of representatives from countries and industry. The S-Mode guideline was submitted to IMO's Subcommittee on Navigation, Communication and Search and Rescue, the NCSR, in mid-October 2018. The 6th session of IMO NCSR Subcommittee completed in January this year a guideline on S-Mode, which will be sent to the next meeting of the IMO's Maritime Safety Committee, the MSC, for approval, which is the 101st session in June this year. So if you thought your work had a complicated organizational structure, the IMO has a more complicated organizational structure. The S-Mode guideline name was changed by the NCSR and are now known as the Guidelines for the Standardization of User Interface Design for Navigation Equipment. These guidelines apply to integrated navigation systems, the INS, electronic chart displays and information system, the ACDIS, and radar equipment. They may be applied to other electronic navigation equipment and navigation sensors where applicable, where it would improve standardization and usability. The aim of these guidelines is to promote standardization of user interfaces to help meet user needs. The guidance within these guidelines have been developed in close collaboration with an international association of equipment manufacturers to ensure its efficient implementation. The guidance also aims to leave room for future innovation and development while still addressing the primary user need for standardization and usability. The following principles were applied when designing the appendices to the S-Mode guideline. Consistency has been identified as the most significant standardization design principle. The use of consistency throughout the design process increases usability. Areas to be considered are standard vocabulary, starboard and port and not using right and left. Secondly, standard symbols and icons, and this should be across navigation equipment. Consistency enables recognition and detectability across the user interfaces of different navigation systems. Thirdly, patterns and groupings. Humans react positively to patterns and logical groupings of items and use categories to search for individual bits of information. And fourthly, standard locations, same place to look at, and this is of course imperative under high workload conditions. Using location and grouping for consistency provides for recognition. Human perception and search works faster with cues than complete recall, especially when aided by consistency. The ability for the user to recognize an event, process, or information flow, rather than recall the detail of how to get to that point, is integral to usability. Sorting, grouping, and location of information according to frequency of use increases efficiency, which is implemented by the use of hotkeys or single operator actions. The integration of humans and technology to support the ability to work as a team relies on them being able to identify the system status. System status provides confidence in the validity of information and the performance of navigational equipment and sensors. Projection to the real world can be exemplified by the sound navigational principle built on using a chart oriented to north up. Information processing research and literature related to chart orientation has shown that a seafarer may find navigational performance improved by using a chart which is oriented to the direction of travel, which means heading or course up. When a frame of reference is not aligned, which means what is seen out the window is not a direct representation of what they see on the chart, such as they are heading south in a north-up chart. The seafarers will need to mentally transform their frame of reference. And research indicates that this requires cognitive processing and an increase in mental workload, which may increase the likelihood of errors. Thus, a frame of reference transformation from true to relative reference of a situation can have an impact on human performance. There are two elements to projection to the real world. The first one is the context to task. Whenever possible, use images or wording that is contextually related to the task. This is applicable to the interaction with the user interface. For example, when increasing a number, twist a dial and show increase as up. The second element is geolocation of information to provide linkage or correlation. What appears on the visual display in terms of location and information is in accordance with the seafarer's understanding of where they are. Continuous testing during development will identify possible error paths that can be removed. Users should be aware of how to navigate back to the start of a process and also be aware of where they are in the current process. And finally, design help functions embedded within systems to be logical, task-focused, user-friendly, and easily accessed and understandable. For example, where a user puts the cursor or a marker on a specific icon, the meaning of the icon may be automatically displayed to help the user. The standardization design principles for electronic navigation equipment are addressed within the S-Mode guideline. The design principles have been applied in the development of the technical content provided in the appendices to these guidelines. And the appendices includes the following. Default settings, which means that a facility shall be provided to apply a set of default settings to return the equipment to a known default state. The default settings are intended to provide a basic and minimal mode of operation for the system or equipment that can be built upon by the user. And you have user settings, which means that a facility shall be provided to store and recall user-specific settings to suit the condition at hand. So for example, when moving from blue waters to littoral waters, the user can change a setting and the navigation display will change in accordance to the actual situation. The hotkeys and shortcut appendix identifies commonly used functions on navigation equipment, and for each function specifies the associated terminology, abbreviations, and where appropriate, icons, as shown on this slide. If available, the recommended to be used for these terms are recommended to be used for the display of navigation-related information to promote consistency of presentation across navigational equipment. The logical grouping of related information appendices defines groups of related navigation information that shall be displayed together on the user interface to enable the user to quickly locate and react to essential navigation information if available on the screen. And as an example here, you can see with the ownership, the following information should be shown. Across requirements for essential information and function states if the information or function should be available by a single or a simple operator action. Single and simple operator action is distinguished by 1 and 2 hard keys or soft keys actions. So single is 1 touch and simple is 2 touches, or a hard key or soft key actions. So the difference between a hard key and a soft key is that the soft keys are different from hard keys because they are dynamic and can be changed, while the hard keys always have the same functions and cannot be changed. The S-mode guidance has been informed by research into human factors, cognitive science, and human-centered design, HCD, as the findings stemming from this research has been seen to be advantages and should be considered as part of system design. This is largely due to HCD affording users quicker and more efficient understanding and familiarization of new technology. Well-conducted human-centered design can also result in error-tolerant systems that can reduce the complexity of tasks while increasing task support. Key elements of HCD are the involvement of a multidisciplinary team, including users, and an iterative approach to design. HCD is driven by knowledge about use, derived from evaluation and testing with users, the results of which drive a formal feedback loop in each of the design stages to ensure usability and safety. E-navigation systems should aim to ensure that navigational and associated tasks are effectively supported, with usability being the measurement that is tested to ensure that this is achieved. The figure shown on this slide outlines the activities and stages that should be undertaken in each of the life cycle stages for an e-navigation system, illustrating the interdependencies of each activity. The HCD process consists of 5 activities: stage 1, stage 2, stage 3, stage 4, and stage 5, and 1 pre-activity to inform development through the life cycle. The pre-activity is to conduct an early human element analysis. Activity 1 is to understand and specify the context of use. It is shown by the C and is a part of each of the 4 first stages. Activity 2 is to identify the user requirements. It is the R and is also a part of all the first 4 stages. Activity 3 is to produce and/or develop design solutions to meet user requirements. So then we are on design solutions, letter D. Activity 4 is to evaluate the design against usability criteria. So then we are on usability testing, the U. And activity 5, the most important, to maintain operational usability. Activity 1 through 4 is part of 4 of the stages, while the 5th stage is related to the operationalization of the system. It's a difficult word. Fundamental to HCD is the collection of user feedback through user testing, which is increasing through stage 1 to 4, shown by the size of the different circles. User testing is an effective means to discover and resolve potential usability and design issues early, as well as throughout the life cycle of a system, by using an iterative testing approach to ensure a safe, satisfactory, effective, and efficient system. Evaluating through usability testing is carried out iteratively at all stages in the life cycle and provides input for future versions of the system. From a human-centered perspective, one of standardization principal benefits, if designed and implemented properly, is in the reduction of the user's physical and mental workload. Reduction in the mental workload has been identified as beneficial in areas such as decision choice, for example, high-risk decision-making under conditions of uncertainty in unfamiliar situation, and information acquisition and analysis, which can be exemplified by the cost of scanning a cluttered display, for example, the Actis. The guidelines support the standardization of user interface design for navigation equipment by providing guidance on frequently used functions, standard symbols, terminologies, and functions accessible by single and simple operator actions. These recommended features were developed through usability tests conducted by the Republic of Korea and Norway, using service, eye-tracking studies, and user interviews. The frequently used functions were identified through a survey administered by the Australian Maritime College and a study using eye-tracking devices conducted by the Republic of Korea. The survey of the Australian Maritime College was held from February to June in 2017 with the participant of 601 seafarers to collect user input on the frequency of use for functions of navigation systems and scenarios in which the functions are utilized. This survey was conducted online, supported by the Nautical Institute, and the results from Australia were combined with results of a study conducted by the Republic of Korea, which was carried out with 33 masters and deck officers on a passenger ferry and on ship handling simulators from April to May in 2018, in order to identify the frequently used functions. Here's here an example of the frequently used functions, and there's also an interesting example from the Republic of Korea eye-tracking study, where we see that 50% of the time the officer of the watch is drawn towards non-navigational related tasks on board the vessel which is transiting from Busan to Osaka, overseas passage. The standardized symbols specialized in the guideline were originally developed by the Comité International Radio Maritime, the CIRM, which is the principal international association for marine electronics companies. Norway conducted an online survey to test the comprehensibility of these icons with a participant of 426 seafarers and combined the survey results with feedback from 5 master mariners. The combined results were used to suggest modification to icons that the research subject had difficulty comprehending. This is an example of such. And the combined results, and in addition, through the simulation test, the Republic of Korea was able to confirm that most of the standardized symbols in the guidelines would be available for the main task of the mariner. The list of functions accessible by single and simple operator actions was also proposed by the CIRM, based on existing performance standards. Norway held an online survey and collected feedback from 107 seafarers regarding the necessary level of accessibility for each function. For each function on the list, survey participants decided whether they believed the function should be accessible by single operator action, simple operator action, both, or not required quick access at all. The Republic of Korea found out most of the standardized symbols in the guidelines needed to be available for the main task of the mariners by the eye-tracking user tests. The Republic of Korea also conducted a test to identify the frequently used functions, and the findings showed that the functions matched the symbols and the single simple operations as identified in the appendices of the guidelines. So this is given to you to show you that there is a thorough research basis on which has developed into the S-mode guideline, which is now to be hopefully formally accepted in the IMO MSc 101st session June this year. The importance of the S-mode is highlighted by the e-navigation strategic implementation plan, update 1, which was issued May 2018 by the IMO MSc. I would like to highlight risk control option 3, which is standardized modes for navigation equipment which supports solution 1, improved, harmonized and user-friendly bridges. Also sub-solution 1.2, which is extended use of standardized and unified symbology for relevant bridge equipment. And sub-solution 1.4, which is standard default settings, save recall settings, and S-mode functionalities on relevant equipment. I would further like to elaborate on these sub-solutions. In order to aid the navigating officer, navigation equipment manufacturers and suppliers are continuously developing their products to include a rapidly increasing number of sophisticated functionalities. As the different suppliers follow different generations and presentation philosophies and impart different terminology, this introduces the risk of the bridge team not being able to access or use all available functions, not being able to produce a familiar setup of the equipment, and consequently not being able to obtain information required for navigational decision-making. Safe navigation relies on the ability of key personnel of the bridge team to easily operate navigational equipment as well as to comprehend the information that is presented to them. Without proper familiarization, which can sometimes take a significant period of time due to the current differences between the operating systems, this is not always the case when someone is new to a particular system. Lack of familiarity with bridge equipment can result in slow or inappropriate responses due to not finding correct information, system status, control functions or alarm, and is therefore adversely affecting the safe navigation of the ship. Standard modes or default display configurations are envisaged for relevant navigational equipment. Such standard modes should be selectable at the task station and would reset presentation and settings of information to provide a standardized and common display familiar to all users. The standard mode should be accessible by a simple operator action, and the standard or default settings would act as a starting point for a user to build the optional settings appropriate for a particular task. Those operational settings could then be saved by the user and recalled later by a single operator action. Standardized information presentation, symbols and coding should be used according to the performance standards for the presentation of navigation-related information on ship-borne navigational displays. There should be a standard or default user interface mode, accessible by a simple operator action, and associated display configuration for relevant navigational equipment. To further exemplify the importance of S-mode, I would like to highlight some of the findings in the MIB report on the groundings of MS OVIT in 2014 in the Dover Strait. The Chief Inspector for Maritime Accidents, Steve Clinch, writes in the report, and I quote, "Unfortunately, the current generation of ACTIS systems, though certified as complying with regulatory requirements, can be operated at a very low level of functionality and with key safety features disabled or circumvented. Training and company culture may mitigate these shortcomings to some extent, but can only go so far. While systems allow individuals to operate them in a substandard manner, there are those who will do so. Such is human nature. For all shipping companies, navigation is a safety-critical function, and failure to navigate effectively can and does result every year in pollution, loss of lives, loss of vessels, and it is hoped, therefore, that the next generation of actors will embody features making them less vulnerable to the vagaries of human performance to achieve a better level of assurance that safe navigation is being constantly achieved." Unquote. I would like to argue that the ASMO guideline enables such a feature. Seafarers express a desire for greater standardization of functionality for navigation displays with regards to human-machine interface, and the S-mode is thus a milestone in achieving this desire. Winston Churchill had many quotes, and one of them being, "Give us the tools and we will finish the job." Many of the tools within e-navigation has been presented to the navigator, but the job is far from finished. There are much work to be done within e-navigation when it comes to the user-friendliness of the benefits of the digitalization on the Maritime bridge. S-mode, as a principle of standardization and simplification for the user, is one important milestone on the way to the full implementation of the e-navigation concept. This concludes my presentation. Thank you very much.
You can stay. This is your corner for the rest of the day. Thank you very much for the presentation, Mr. Hareide. Are there any questions for the committee? You are saving the question for the next session. And are there any questions from the audience? I will also allow tricky questions. Somebody from the back. Yes, go ahead.
Navigation Center. I would like you maybe to comment on the risk of lower situational awareness due to the complacency with all the systems that should give you, or could give you a good overview of the situation.
It is an interesting question, and if I understand you correctly, when relating to myself as a navigator, while spending maybe 12 hours a day looking at the displays, which I probably knew 5% of the functionalities within. I never read the manuals. It's kind of how navigators work, I think. And this is an important move within the e-navigation concept, that the users has to understand the meaning and the functionalities within the system, because I would argue that with the concept of e-navigation, one of the parts of the navigator's situation awareness is system awareness. And understanding of how a system is built, its possibilities and limitations, is imperative for the navigator to achieve a higher degree of essay. And when it comes to complacency, if you mean that navigators are lazy, is that what you mean, or that we tend to be lazy? Was that, or did I understand you wrong?
Well, it was not wrong, but my opinion is that there is a choice to use the systems.
Yes.
And I heard that somebody says that all these systems will improve your essay.
Yeah.
And it could improve your essay, is my opinion.
I have a strong belief in the humans, and I would argue that the humans are the most important tool at the ship bridge. The problem for some time has been that the human has got a lot of systems that has been provided to them on the ship bridge, which is said to improve their situation awareness. And most of them do, but as the operators don't understand the usage of the systems, exemplified by the MS Ovid, where they set the safety contour shallower than the draft of the vessel, and then the vessel grounds in a area which on the chart appears to be safe to navigate on, then I would say that this is complacency. But I wouldn't blame it on the humans. I would blame it on the industry and the organizations around the ship owners, which doesn't invest in the humans. And that also for us as an academic institution needs to realize this and provide thorough understanding for our navigators when they come out and get born again on board the ship bridge of a frigate or a corvette. I would say that it's very important.
Thank you, Mr. Hareide. You still have to be in your corner. The committee will now decide if the trial lecture was satisfactory. If so, the thesis will be defense can take place 1:15 in this room. The trial lecture is now formally over.
Thank you.
Please be seated. Professors, associate professors, doctors, candidate, colleagues and friends of academics, electronic navigation and naval operations. My name is Bart Eriksen, commander of the Royal Norwegian Naval Academy. On behalf of the Chief of the Navy, Admiral Stensønes, and the Superintendent of the Norwegian Defence University College, Admiral Dedichen, I welcome you to the Royal Norwegian Naval Academy. This is a great day for us in many ways. It's a disputation on a highly relevant topic. We emphasize the link between academics and naval operations. We also strengthen the network of the maritime domain, naval operations and different universities. The Norwegian University of Science and Technology, the University of Tromsø, the Western Norway University of Applied Science, Gdynia Maritime University, and the Norwegian Defence University College. We are really looking forward to the rest of this day now, so welcome to all of you. And by these words, I would like to give the word to the chairman of the committee, Professor Hildre.
Dear committee, candidate, colleagues, ladies and gentlemen, the trial lecture is approved. First step. On behalf of the National Joint PhD Program in Nautical Operations, the Norwegian University of Science and Technology, and the Royal Norwegian Navy Academy, I would like to welcome you all to this public defense of the thesis submitted by Odd Sveinung Hareide for the degree of Philosophy Doctor at the Faculty of Engineering, Department of Ocean Operation and Civil Engineering, Norwegian University of Science and Technology. My name is Professor Hans-Petter Hildre. I'm head of the Department of Ocean Operation and Civil Engineering at NTNU. And I am appointed to moderator for this public defense. The program board for the National Joint PhD Program in Nautical Operations granted Mr. Hareide admission to this PhD program on the 15th of December 2016. The main supervisor has been Associate Professor Runar Osnes at the Department of Ocean Operation and Civil Engineering, Norwegian University of Science and Technology. Mr. Hareide submitted his thesis on the 9th of September 2018, entitled The Use of Eye-Tracking Technology in Maritime High-Speed Craft Navigation. The following committee was appointed: Professor Adam Weintritt, Gdynia Maritime University in Poland; Professor Margareta Holsdotter Lutzoft, Department of Maritime Studies, Western Norway University of Applied Science; and Professor Hans-Petter Hildre, Department of Ocean Operation and Civil Engineering, NTNU. The evaluation committee decided on the 11th of March 2019 that the dissertation was worthy of being defended for the degree of philosophy doctor. Earlier today, the candidate presented the required trial lecture on the assigned topic as modes as one of the important milestones on the way to full implementation of the e-navigation concept. The committee has found the trial lecture satisfactory. The public defense will now start with Mr. Hareide giving a presentation of his thesis. After Mr. Hareide's presentation, there will be a 5-minute break. Important. During this break, anyone who wants to pose a question regarding the dissertation must approach me. Only questions announced in the advance will be allowed. Now, I ask Mr. Hareide to present his thesis. Please, Mr. Hareide.
Thank you. Distinguished committee members, supervisors, vice dean, commander, colleagues, and my dear friends and family. Welcome to this PhD defense with the topic the use of eye-tracking technology in maritime high-speed craft navigation. I will first explain how maritime navigation is undergoing a paradigm shift with the introduction of electronic navigation with vast amounts of information available, and put this into context for the high-speed craft navigator. I will further show how a control strategy and situation awareness is essential for the navigator to conduct safe and efficient navigation. I will elaborate on the most important findings in the 5 articles in my thesis before concluding with the contributions and further work to be done. Doctoral candidates have a tendency for falling in love with quotes, and mine originates from Nathaniel Bowditch in the book The American Practical Navigator, first published in 1802, and I quote, "Marine navigation blends both science and art. A good navigator constantly thinks strategically, operationally, and tactically. He plans each voyage carefully. As it proceeds, he gathers navigational information from a variety of sources, evaluates this information, and determines his ship's position. He then compares this position with his voyage plan, his operational commitments, and his predetermined dead reckoning position. A good navigator anticipates dangerous situations well before they arise, and always stays ahead of the vessel. He is ready for navigational emergencies at any time. He is increasingly a manager of a variety of resources, electronic, mechanical, and human. Navigation methods and techniques vary with the type of vessel, the conditions, and the navigator's experience. The navigator uses the methods and techniques best suited to the vessel, its equipment, and conditions at hand. Some important elements of successful navigation cannot be acquired from any book or instructor. The science of navigation can be taught, but the art of navigation must be developed from experience. With this as a backdrop, I will continue the talk with looking at the recent developments within maritime navigation. Digitalization is transforming the maritime ship bridge and is regarded as a paradigm shift in maritime navigation, exemplified by the change from paper charts to electronic navigation. And at my department, the Navigation Competence Centers, we have a saying that we have moved from 6 knots and a sextant to 60 knots and Bill Gates. The traditional navigator skills have been challenged with the introduction of integrated navigation systems. But as we have learned from the possibilities and limitations of technology, it has become clear that the craftsmanship of navigation is still needed. However, it is clear that the increasing amount of technology induces a change in the competence requirements for the navigator. The navigator has always had an important role in conducting safe navigation, exemplified by this random navigator. And the main job related to navigation has been to find and fix the position to keep the vessel safe. With the introduction of electronic navigation, the vessel's position is provided in more or less real time. The navigator's role has changed from finding and fixing the position to monitoring the position presented in the navigation system. This has been an important move for the safety at sea, but new challenges such as active-assisted groundings have emerged. This led to a discussion of the role of the navigator in integrity monitoring of the navigation system, which further demands a certain level of understanding of the sensors and systems in use. It is important to utilize the strengths of the human navigator. Before continuing, I would like to highlight some terms that are much used in the talk. Navigation is the process of monitoring and controlling the movement of a craft or vessel from one place to another. A high-speed craft has a formal mathematical definition in the High-Speed Craft Code, but is generalizable to any vessel operating in speeds above 20 knots or approximately 40 kilometers an hour. So, high-speed craft navigation is then the process of monitoring and controlling the movement of a craft with speeds exceeding 20 knots from one place to another. And finally, electronic navigation means navigation conducted with the use of electronic aids or instruments. The modern ship has a wide variety of sensors that are integrated and connected through various networks, and this is a schematic of the navigation system on board a platform support vessel. To simplify the setup of a navigation system, I prefer using this schematic. Different sensors, such as position, heading, and speed sensors, are integrated to the human-machine interface, the navigator, through displays in the ship bridge. The amount of sensors integrated and connecting within the navigation system is variable dependent on the ship type and size. All of these sensors has their advantages as well as limitations, which should be known and understood by the navigator to better interpret and evaluate the information provided on the multifunction displays to the navigator. The sensor's information is presented in 3 main applications on the multifunction displays, the MFDs on the ship bridge, which is the radar, radio detection and ranging application, which is a terrestrial navigation system using radio waves to determine range, angle or velocity of objects. You have the conning application, which aim to make key information available for efficient monitoring. Conning information gather all relevant sensor information and navigation data at a glance and aims to improve accessibility for the navigator. And finally, the electronic chart display and information system consisting of the digital chart and integrated information from the sensors connected to the navigation system. This is a picture of the electronic chart display and information system, the ACTIS application, shown on one of the multifunction displays on a ship bridge. The modern navigation system is arguably a complex system as information overload is endemic. Sensors are interconnected in systems and information is integrated and presented to the navigator. Research has shown that there are a growing concern related to the amount of information in each display and also regarding the total amount of displays on a ship bridge to collect the information from for the navigator. Most of the navigation systems aims to support the situation awareness of the navigator. I would like to put high-speed craft navigation into context for the audience. This movie shows the different challenges when navigating in high speeds in demanding littoral waters. The conditions are changing and challenging, and the work and communication in the navigation team is imperative for safe and efficient navigation. The movie is a time-lapse from a high-speed craft passage with a corvette in littoral waters. High-speed craft navigation is recognized by the challenges induced with higher speeds. With higher speeds, the time to conduct the decision-making process of the navigator is decreased. The level of difficulty will also increase with the confinement of the waters in which the vessel operates. The decision-making process is known as a control strategy for the navigator and is an iterative process. The control strategy developed by the Royal Norwegian Navy is known as the phases of navigation and is shown in this figure. The four phases of navigation is a continuous iterative process during the passage and consists of the preparation, turn, control and transit phase as shown in the figure. And all phases has related tasks to conduct for the navigation team. This control strategy is developed in order to support the role of the navigator as an integrity monitor of the systems, as the navigator can compare information from visual sites with information from the navigation systems. Note that the four phases of navigation are utilized after a thorough planning process of the voyage has been conducted before it starts. The methodology fits any type of vessel, but the process is more demanding in confined waters and with higher speeds. One of the purposes with integrated navigation systems, INS, is to support situation awareness, SA. But what is situation awareness in the context of the maritime navigator? Situation awareness, SA, is basically to be aware of what is happening around you and understand what that information means to you now and in the future. One of the most known researchers, Mika Ansley, defines 3 levels of SA as, and I quote, the perception of elements in the environment within a volume of time and space, the comprehension of their meaning, and the projection of their status in the near future. Another researcher working primarily within aviation, Wickens, has argued that Ansley's work has been important, but that the construct of SA is not good without context. He further argues that SA consists of 3 components: spatial awareness, task awareness, and system awareness. All these 3 components have impact in the real world dependent on the domain. Spatial awareness concerning the environmental factors such as weather, task awareness for mission assurance, attention and task management, and system awareness for keeping the operator informed about status and actions that have been carried out by automated systems. As shown in the video earlier, dependent on the context, the complexity in maritime operations are high. With the increase in speed and more use of technology and displays, the importance of a high level of SA for the maritime navigator has been underlined. The figure on this slide presents the contextual model for the maritime navigator's SA and consists of spatial, task and system awareness supporting the navigator's overall SA. The concept of spatial awareness is inherent in the task of moving a vessel through a space filled with hazards. The environment represented as hazards, and in demanding littoral waters, the topography is challenging. This could be represented by underwater rocks or by headlands or islands hiding other vessels or dangers as the journey progresses. The weather, waves and tides constitutes an alternating challenge, which the navigator has to notice, comprehend and project the status of to keep the vessel safe. Task awareness in the maritime domain includes the mission and further SNCS, which I will explain, S for seamanship, which implies the control of the vessel, N for navigation, navigating safely from A to B, C for communication both internally and externally, and S for systems management. Conflicting task requirements, unexpected events, and several cognitive tasks challenge the navigator's task awareness. The modern ship bridge has complex and dynamic systems. One such system of several subsystems is the integrated navigation system, the INS. Increasing computer power has enabled the navigation system to perform many actions: status monitoring, integrity monitoring, automatic target tracking, and automated track control. In addition, the threat from maritime cybersecurity, MCS, has arisen with the increased use of computers, together with the close coupling between information communication technology and operations. The complexity of the vessel's navigation system, coupled with poorly designed systems, makes system awareness difficult to maintain. The navigator's assay model is outlined in this figure and is established to form a degree of applicability of assay to the real-world problems faced by a high-speed craft navigator operating in demanding littoral waters. Note that the maritime system is an open system with an uncountable amount of variables. The variables mentioned within spatial task and system awareness in these figures are some of the variables that the navigator has to notice, comprehend, and project the future state of to achieve a high degree of assay. Eye tracking is the process of measuring where one is looking, the point of gaze or the motion of an eye relative to the head. This collected data is known as eye tracking data, collected by eye tracking technology devices for measuring eye position and eye movement. Eye tracking glasses is an eye tracking technology which is mounted in a pair of glasses. This is one of the eye tracking glasses that I have been using. It is the Tobii Pro glasses, second generation eye tracking glasses. So it consists of the glasses and a recording and battery device. You mount the eye trackers to the participants, calibrate the glasses, and then you start the recording. You can also monitor the recordings from a tablet at any given time, store it, and then the large job with the analyzing starts afterwards. The data collection has been conducted both in simulator and field studies on board the Royal Norwegian Navy's corvettes. A total of more than 11.5 hours of eye tracking data has been recorded and analyzed. And as a rule of thumb, 10 minutes of eye tracking data takes 1 hour to analyze, making the analyzing a resource-demanding process. In addition comes the time used in statistical programs to further interpret the eye tracking data matrix. Areas of interest can be defined in the eye tracking data and are known as AOIs. They can be used as a tool for the further analysis of eye movement data. AOIs define regions in the stimulus where the researcher is interested in gathering data. And AOIs also allow for further events to be defined and detected, such as total time in a specific AOI, transitions between AOIs, and AOI hits. The AOIs defined in my thesis is the outside of the vessel, the surroundings, the electronic chart display and information system, the radar, and the conning. Visualization maps of attention, such as heat maps, focus maps, sequence charts, and scan patterns, can be used to represent eye tracking data. It does not represent attention per se, but the spatial distribution of eye movement data. It is important to note that the spatial distribution is conducted over time, while this visualization is done on a picture of any given time frame. Attention maps can provide quick, intuitive, and in some cases objective visual representation of eye tracking data, from which can provide an immediate grasp of meaning. The most reported and known event is in fact not related to a movement, but to the unmovable eye, and is known as a fixation. A fixation is the state when the eye remains still over a period of time. For example, when the eye temporarily stops at an object during a visual scan of the outside environment. In this figure, you can see the fixations represented by the circles, and the size of the circles represent fixation time. Larger circles, larger fixation or higher fixation times. And the lines between the fixations are the saccades. In this picture, we can also see the 3 suboptimal design issues identified by eye tracking data. The first one was the poor availability of the heading bearing in the radar graphical user interface. The second one was a challenge with human-computer interaction with the trip meter. And the third one was suboptimal graphical user interface in the route monitor tool in the electronic chart. Heat maps visually display the areas where the participant looked, which implies which areas are important for the participant. In this figure, the average fixation time is given in milliseconds. The average time is color-coded, where the bright yellow code indicates short fixation time, about 200 milliseconds, and the color red indicates long fixation time, about 2000 milliseconds. Visualization maps, such as heat maps, have been used in an inordinate amount in eye tracking research, and it is important to understand the possibilities and limitations by using heat maps. Heat maps are a very good start in exploring where to conduct further analysis, but must be taken as part of an entire process. Appraising a heat map alone can be a root of all sorts of misreads. Heat maps and focus maps are related, and focus maps visually invert heat maps to enable the visibility of the areas of viewer attention. As shown on this figure, focus maps are negative space correlations, visualizing the negative space of the corresponding heat maps. Heat maps and focus maps are two related standard techniques that are useful for providing a synaptic view of eye movements aggregated over time and subject. Pros and cons with the use of heat maps and focus maps are similar, and in their basic configuration, heat maps or focus maps cannot convey the temporal order of eye movement. Sequence chart is a visualization technique to better analyze the visual distribution in time concerning the different AOIs on this axis and time on this axis. The sequence chart shows the order and duration of dwells in the specific AOIs and has proven valuable in usability studies. And not all ETG manufacturers have sequence charts in their software. In this sequence chart, you can clearly see that the route monitor information tool and the trip meter is taking a lot of the time for, or a lot of the attention of the navigator, which was an interesting finding which I used in my work. The lesson learned from pursuing electronic navigation has led to this thesis, and we used the following tools to address research questions in the thesis. We used the bridge navigation simulator here at the Naval Academy at the Navigation Competence Center. We used the high-speed craft, the Royal Norwegian Navy corvette, which is known as the Shoal class. We used eye-tracking glasses, and the most important tool is, as always, the human resources, the navigators of the Royal Norwegian Navy corvette service. The question we asked us were, can eye-tracking data be used to evaluate and compare the effectiveness of live and simulator-based navigation training? Can eye-tracking data be used to map and better understand the visual attention of the high-speed craft navigator? And is the visual scan pattern of the navigator optimized in order to facilitate integrity monitoring of the navigation system? And finally, can eye-tracking data be effectively used in the evaluation of the navigational bridge design and the corresponding user interface? And further, if eye-tracking data can be used to validate a design review of a maritime high-speed craft bridge. The first article was a comparative study of the Shoal class bridge and simulator navigation training. And the aim of this article was to present a comparative study of bridge navigation and simulator training to evaluate possible disparities between bridge simulator training and onboard training. Findings indicate that the use of a one-to-one bridge simulator is efficient when it comes to navigation training and provides the same training outcome as onboard. It has been identified that the average fixation time in the outside is higher in the simulator, and a lower fixation rate also indicates that the use of a bridge simulator involves a more demanding cognitive process, leading to a higher mental workload for the navigator. Instructors should consider this when designing simulator navigation scenario. A higher degree of details in the simulator database and a higher simulator display resolution could compensate for this distinction. The second article in this thesis was a maritime usability study by analyzing eye-tracking data. This article shows how eye-tracking data with a defined method utilizing scan path events and attention maps can be used to identify which areas of interest attract the navigator the most. The dataset presents an example of suboptimal bridge layout concerning placement of equipment, together with two examples of suboptimal graphical user interface in radar and Actis software. The eye tracking data identifies area of interest which drew too much of the visual attention of the navigator, and we have presented suggestions for improvement in the bridge layout and software user interface based on the findings. Eye tracking data shows good potential for analyzing the usability of a bridge layout and software user interface on a ship bridge when using the correct methods. Advantages and limitations with using eye tracking glasses, and these two different types are laid down, with emphasis on the importance of not affecting the normal behavior of the participant, and also how the software should provide good visualization and interpretation of eye tracking data. One of the most interesting findings in Article 2 was related to eye tracking numerosity measurements known as ScanPath events. Lookback are operationalized as saccades to areas already looked at, and is also known as returns. Lookbacks are closely related to inhibition of return, which is the observation that attention is unlikely to be redirected to previously inspected areas. A lookback could constitute a failure of memory, but one must also account for the working memory has a limited temporal capacity. Lookbacks can also indicate that the user is double-checking the information in the given area and could be interpreted as the importance of information in the given area. Whether and when looking at how often a participant is rechecking the content they were seeking in an area could imply a difficulty in understanding its content for a specific user attraction. The number of returns could also indicate a semantically informative area. In a complex scenario like the Maritime Bridge, the lookback or returns will indicate the importance of the AOIs. And the outside and actives are presented with the highest amount of lookbacks, and an interesting observation is that the actis has a relative higher amount of lookbacks compared to dwell time, which can indicate poor usability. A backtrack is the specific relationship between two subsequent saccades where the second goes in the opposite direction of the first. This behavior can be indicative of confusion or uncertainty. For usability studies, one could argue that using backtrack is a better representation due to changes in goals and an indication of a mismatch between the user's expectation and the interface layout. With the AOIs defined in this study, a backtrack will be interpreted as an eye movement from the actis to the outside and back to the actis. That's a backtrack. This can indicate that the navigator finds it challenging to interpret the information in the area and thus needs to backtrack to the area to validate the assumption. The amount of backtracks in the figure above is given in percentage to identify the relative relationship between the different backtracks. And we see that more than 50% of the backtracks is concerning outside and the actis, which could represent a challenge for the navigator to interpret or understand and to memorize the information given from the actis. This further drew our attention toward the efficient use of scan pattern for the navigator. Inspiration to the maritime scan was collected from research in aviation, as the efficient use of scan patterns has been known and used for other professions than the maritime. Defining a recommended scan pattern for the maritime navigator in relation to different meteorological conditions can contribute to a more efficient interaction between the navigator and the navigation system. This will provide increased situation awareness for the navigator and thus provide a safer passage. And the recommended time in the different areas of interest are shown on this analog flip over. And you have visual sailing mode and you have conventional sailing mode, which is under bad weather conditions. And you have the AOIs, outside, actis, radar, and conning. And remember, it's just a rule of thumb. The maritime scan consists of two subparts, where the first consists of the outside scanning of the environment, and the width of the scanning arc is based on the collision theory of Ruben Greppner-Takle, and by dividing the scan into blocks and conducting a front to side scan. A better situation awareness is expected. The second part consists of the sensors and systems data in the navigation system. And this data is integrated and presented in the 3 applications ACTIS, radar and conning. The scan is conducted to increase awareness of the navigator's role in integrity monitoring of the systems in order to identify if there are any errors or biases in the sensors or system. The amount of time in each of the subparts will vary with regards to the meteorological conditions, and this is just presented as a rule of thumb. The use of the maritime scan will better utilize the spatial and system awareness for the maritime navigator. And as a consequence, situational awareness will increase, which will enhance safe navigation. The 4th article was in order to develop a high-speed craft route monitor window. The method used in the article is a combination of the eye-tracking data collected in the preparation of paper 1 and 2 and the use of the human-centered design process within a technical working group. The technical working group consisted of end users, software manufacturer engineers, and human factor specialists. The route monitor information is vital for the navigator, and the Royal Norwegian Navy has established a standard operating procedure, a SOP, in order to support the navigation team in establishing and maintaining a high degree of SA in order to support safe and efficient navigation. The SOP is aligned with the decision-making process in navigation, known as the phases of navigation. Current information holds vital information for the navigator in the control and turning phase. You have the current heading, which is aligned towards the planned course. You have the current sail distance aligned with the planned leg distance, and you have your current heading mark, which you use in the control phase. Future information is aligned with the communication procedure and holds vital information for the navigator in the preparation phase of the next turn. You have the time to the wheelover point, which is calculated based upon speed through water. You have turning information, next course and distance, what your next heading mark is. Provide remarks such as dangerous sea areas, radar notations or similar. And you have the cross-track distance and the turning radius of the vessel. This work resulted in the development of a beta version of the route information tool in the Kongsberg ACTIS, implemented in version 8.01. The 5th and final article in this thesis is named Validation of a Maritime Usability Study with Eye-Tracking Data. The aim of the verification study was to measure if the suggestions for improvement of bridge layout, design and software interface analyzed and outlined in paper 2 and 4 and implemented in the midlife update of the Sjøkrigsskolen corvette had been effective. The upper figure is the scan pattern of the navigator before the midlife update of the Sjøkrigsskolen corvette. And the lower figure is after the midlife update. With the eye-tracking data collected in this study, the midlife update aimed to remove 3 suboptimal design issues, which was the poor presentation of the heading bearing, the human-computer interaction difficulties with the trip meter, and the route information tool. Analyzing the visualization maps with emphasis on the scan path, there is a clear indication of a tidier scanning pattern for the navigator, and it adheres to the recommended scan pattern for the maritime navigator. Areas outside ACTIS and radar are the main focus area, and there are less fixations in the less important areas. From the heat map analysis, there is a clear indication that the ACTIS is divided into 2 sub-areas, the chart and the route information tool. The aim of the design revision was to support more attention towards area outside, and the post-midlife update data set indicates the contrary. To better understand this finding, a thorough analysis of each participant was conducted. The span in experience level in years as navigator and experience level with the new software has a clear indication of being an important variable to the results of eye-tracking data analysis. To highlight the extremes, the most experienced navigator with the most time on the new software was compared towards a less experienced navigator which was not familiarized with the new software. The results showed a 41.3% difference, almost 50% difference in attention directed towards the surroundings of the vessel. This provides a clear indication of the importance of familiarization with new software in general, and especially before a validation of a design review can be conducted with good validity. It also highlights the importance of experience as a factor when addressing changes to or new software. Finalizing this talk, I would like to highlight the main contributions in the thesis. A one-to-one bridge simulator training has been evaluated towards live navigation training with the use of eye tracking data and is assessed to provide similar training outcome. Improvement of the design of navigation training simulator scenarios has been suggested. A better understanding of the high-speed craft navigator's visual attention distribution has been established with the use of eye tracking data, and a proposed scan pattern for the Maritime navigator has been established. The use of eye tracking glasses to collect eye tracking data in maritime usability studies has been proven useful, and the use of the human-centered design process as a tool in the design and design reviews of bridge design and navigation equipment software is recommended. Better information management for the modern navigator by developing an improved route information tool, the high-speed craft route monitoring window, through developing has been implemented from Cambridge version 8.1.3, which also outlines the importance of familiarization with new navigation software and equipment, supported by eye tracking data. Better understanding of high-speed craft navigation through developing a control strategy for the conduct of a passage, the phases of navigation, has been presented. This has been done in conjunction with establishing a contextual SA model for the navigator. With the knowledge gained through the analysis of the eye tracking data, an update of the Royal Norwegian Navy curriculum in electronic navigation has been conducted in the subjects navigation systems, military navigation, and in the curriculum of the Shoal Class Officer of the Watch course. As I have realized at the end of the work of this PhD, the PhD is not the end, but the beginning of further research. I would like to highlight two areas which I believe will improve the safety of navigation with the use of technology. Bridge navigation simulators has been evaluated to have a significant impact on the training of new and existing navigators, and eye tracking technology can further enhance the efficiency of this training. The possibilities in the use of remote eye tracking technology systems in the training of navigators on bridge navigation simulators to provide increased efficiency in training should be further investigated. Information management is challenging for the modern maritime navigator. Further investigation into technology on how to reduce the head-down time for the navigator by shifting the visual attention towards the outside of the ship should be investigated. This could be done by the use of maritime augmented reality. This concludes my presentation. Thank you very much for your attention.
Now it is a very short break. If you like to stretch your leg, it's okay, but don't go away, but you can stand then. You ready? 5 minutes. We will now continue with an opposition. We will start with the first opponent, Professor Adam Weintritt, who will present his opinion on the thesis, and the candidate will be allowed to answer the comments and questions from the opponent. Then, the second opponent, Margareta Lutzok, will continue.
Mr. Chairman, ladies and gentlemen, my name is Adam Weintritt. I work for Gdynia Maritime University, and I am 35 years in the field of EGDIS, so modern navigation. And my second name is opponent number one. And before I start to play like an opponent, I must say that my general observation is positive, very positive, and I like your fresh point of view. But the title of your PhD thesis is the use of the eye tracking technology in maritime high-speed craft navigation. Your main supervisor was the Professor Runar Ostnes, and the co-supervisor was Professor Egil Pedersen. But in February issue of the monthly magazine Coordinates, this one, was published article titled Marine Augmented Reality. But surprise, surprise, the co-authors of these articles are Sveinung Hareide and Professor Thomas Porate. The question is, why Professor Porate? What was the role of the Professor Porate in preparation of your PhD thesis?
Professor Thomas Porate is a professor in interaction design at NTNU. The background for the cooperation with Porate is that we have been involved in an industrial project called Maritime Augmented Reality, where the Navigation Competence Center has been invited to participate to look at the possibilities of AR in the maritime world. So that was where I met Professor Porate. He has also had a PhD thesis on the egocentric view, like I talked of during the S-modes, that we have the egocentric view and the exocentric view of navigation. So I've had many interesting discussions with him. So that's the background for him being part of that article.
So thank you very much. That's I wanted to hear. Yeah. And the second general question, what is your opinion about whether this new modern technology, augmented reality, eye tracking technology, in any way can be dangerous for human health, for the psychical and psychological balance of the training person? Is this technology really safe for training? The question is, before some trainee, after using this new technology, feel like after using the merry-go-round or roller coaster?
When looking at AR, it's I think that there has been a mix of definitions within this concept. You have both virtual reality and you have augmented reality. And virtual reality is then exemplified by fixing your phone in a glasses and you put them on, and then you have a lot of motion sickness and issues regarding that. AR is projecting information on glasses. So it's basically taking this projector and keep very small and projecting onto glasses. The reasons for us finding this technology interesting was that we wanted to reduce the head down time for the navigator. As seen on the movie, you see the navigator constantly seeking information in the electronic chart, and you also see that he has to go very close to the electronic chart because information is difficult to access. Therefore, we looked at other domains. We looked to aviations, and sadly for the Royal Norwegian Navy, but gladly for the Air Force, we have acquired new fighter aircrafts F-35. And in aviation, AR has been used for quite some times, and I'm actually not sure for how long time, but it has been used for a good period of time. And they are curious about why we don't use it in the maritime domain. So this kind of got us to start to look at these things, and I am sure that there is a lot of limitations with the use of AR as it is today. You have the most traditional AR today is the Microsoft HoloLens. Maybe many of you have seen one. It's almost half a kilo, and you mount it to your head, and it's like wearing a helmet. So it's not good for a constant use for the navigator. You get pain in your neck and things like that. So for the health, it's not good. But this is not operationalized. This is still in a research project, and as we see within this technology, the technology is accelerating very fast, and especially with the use in commercial off-the-shelf equipment. So we believe that the boundaries of the physical boundaries of AR will be eliminated with time. But as you say, it is important that we put further research into how this will affect the navigator. And one thing being is light pollution, for example. For a navigator, night vision is paramount, and using a projector and projecting light very close to the eyes is of course not good for the night vision. But this is also possible to mitigate. Looking for words.
So thank you. So I will continue. The first title of your PhD thesis was the use of the eye tracking glasses in high-speed craft navigation. And according to my suggestion, you decide to change the title of your thesis into the use of eye tracking technology in maritime high-speed craft navigation. But our suggestion was to change to in high-speed craft navigation. So just now it's much better, but the question is there any change? Is there any change between the maritime high-speed craft navigation and high-speed craft navigation? And also I have some objection to the definition of high-speed craft which you use in your thesis on the page number 2. Page number 8 terms. Your definition is very short, but definition which you use in the IMO is much longer. Exactly. Thank you. You can stop. I am happy. So, I am very traditional man, and first time I observed during the defense of the thesis some movie with so strange music. But the question is, who is the author of this film? It's your film?
No, it is one of the captains on the Royal Norwegian corvettes, Anders Jacobsen, has very kindly allowed me to show the movie, and he made the movie during, I think this is right, Stefan, during his control phase of being a commander of a Skjold class corvette.
I don't remember when he made it.
Okay, so he kindly presented it to me.
So it was my joke, I am not engaged. So in the last question, just particular, before this film you present a few slides. Could you present the slide number 3? On the very beginning.
Yeah, I'm getting there, slide number 3.
Yeah.
The first,
and
this
according
one.
to the
This one?
According to the definition of EGDIS, the positional information must be connected with EGDIS, but the rest is an option. So I have some objection. This information, which is in the left upper corner, should have a different status than the other sensor.
I agree.
If you agree, I am happy and I am finished with my question.
How nice, you make me the bad guy.
Yes.
To elaborate on this question, the position is very, like I said, for the navigator it's gone from find and fixing to monitoring the position presented, and it's presented through the global navigation satellite systems, which is satellites that provides more or less in real time the position of the vessel, and that is the imperative position sensor in the navigation system. And that's correct. I am wrong in this.
I didn't get the printed version, so it's a well-read copy, and you see all the red marks. Odd. You are passionate about technology and navigation, so we will talk about humans and philosophy. Mainly. I'm going to focus mainly on the human performance issues in the beginning of your background chapter. Very quick connection to eye tracking, between human performance and eye tracking, possibly visiting HCD, and then one or two questions about the method discussion, if we have time. When I did my defense, there was no time limit. People tell me it went on for 5 hours. I have absolutely no idea. Because when you're in it, you don't feel it. And when I looked at the first section of 2.3, it's clear that it's from Wickens. And he is, as you said, an aviator and an engineer, or possibly engineering psychology. He discusses something called human factors from the neck up and human factors from the neck down. Have you seen that?
No.
Do you know what he means? What do you think about that division?
That you utilize the human strength by using the brain. Is that by neck up, or?
I think what he means is that you can make a split somehow, that this is human factors and the rest is ergonomics. And the correct answer, of course, is you can't split the thinking and the action anyway. And that's connecting to something that you say, actually. You say several cognitive phenomena are not directly reflected in performance. This is going to be quite theoretical. Do you know what that means? Could you explain that a bit? Because what you're doing is measuring performance in eye tracking, and you're saying something about a cognitive phenomenon. So I'm looking for the link between these.
Okay. Yeah. Well, the links between the eye tracking data and the cognitive is debated. I have been using one Swedish researcher, Holmqvist, which seems to be one of in the frontiers of the use of eye tracking technology. And like I tried to outline with the lookbacks and the backtracks, there are relations between the eye movement and cognitive processes, but it could be different relations. It's impossible to say that this eye movement indicates this cognitive phenomena. It could be several cognitive phenomena. Was that the answer to your question?
It's partly because we're also talking about the connection between eye tracking and visual attention.
Yeah.
I know you even quote a paper where they talk about looking isn't seeing. It's just because your eyes are resting somewhere. We all know we might go into some kind of screensaver mode, and your eyes are.
Yeah. That's.
Doesn't mean maybe I don't even see anything.
And I think that is a very important thing to be aware of for the navigator as well, because when we looked at the maritime scan pattern. When I relate to it myself, I have several times sat on the bridge or in a vehicle, and you just stare out the window. You're not looking to find something, you just stare, and then you probably won't find anything. While the maritime scan is a theoretical framework of how you should use your brain and your vision to actually find something, so that you're not just seeing out the window, you're actually looking to find something.
Yeah, there is. We could connect to that, the maritime scan, because what I was thinking of is in aviation that was actually used to change the design of the cockpit, but you're using it to change the training.
Yeah, and I think that you are onto something important, because I actually discussed it with some of the pilots that are here in the break, that something that is good and bad with seafarers is that we adapt to the tools that are given to us. We don't question them. You throw stuff on the bridge and we just, okay, it's put down in the corner there, that's probably where they wanted to put it, so then I have to walk down there to use it, instead of say, no, I won't take this ship off the quay before the equipment is in the right position and all the ergonomics and everything and the training and you name it is in order. A seafarer doesn't see a problem. He just finds the solutions and workarounds and adapts to the situation. And I think the more I think of it, the better I think that it is. But at the same time, it makes the job done. But if you look at aviation, in parts of my research, I went in a plane and I sat in the cockpit and spoke to them, and we live in two different worlds.
Yeah.
It would not be a question to just jump into an aircraft, a 737 MAX coming from a -8 and fly it. It's very procedural, and safety measures are always in place. So I think that, and I have probably partly fallen into the same trap, because we have a system. I want to make this shit work, and this was the best I could do with it. But maybe we should tear it all out and start all over again.
I know that is the problem, and to connect what you say, nobody would walk into a cockpit with an AIS and say, where can I put it? And they did that in ships.
Yeah.
And connecting back to this picture, when I wrote my thesis, what I found then is that the human operator was actually the sensor integrator. And probably very, very much so today, maybe not on all ships, so I'm just wondering, what is this, just sort of a generic picture of a navigation system or a wish list?
Yeah, it's more of a generic schematic, because always you find these types of schematics which I hardly can relate to, and if I ask the audience, they probably can't relate to it. So I try to make a general schematic like this with all its limitations. But what we do have now is that we have a larger extent of a new layer, which is called sensor integrators. They call it MUX, they call it all different types of things. So they connect all the sensors into one computer, and they mix all the data to provide better data. And it sounds kind of irrational, doesn't it? That they take data and makes it better, but they say that they do, so I accept it. And it's Kalman filtering and all that stuff, which...
You went into the same trap again. The engineers walked all over you.
Yeah, that's probably true. Back then, but not now, of course. Now I know better.
No. So this is kind of a model metaphor of a...
Yeah, but I also agree with probably not shown in a good enough way, but the role, I call it integrity monitoring. It's probably related to your wording as sensor integrator, but as the most simplest example, we have done tests where experienced navigation teams conduct a passage in a well-known fjord, and we deviate the position of the vessel, the GPS position, they look out, they look at the screen, they see that it doesn't match, but they think it's strange, but the axis has always been correct, so I'll wait for some time before I flag any deficiencies on this. And in the most extreme cases, the error has been 2,000 meters in littoral waters, and it's and that's the navigator has to trust himself as an integrity monitoring, and when he sees anything that does a mismatch, then he must take action. That's kind of the integrity monitoring part.
Okay. To be able to describe these systems, because you can see all the details on top here, and then we've just got an orange box called human, and yes, we're gonna go there. You use the metaphor of information processing to describe a human, well, partly, because then you said the human is an information processor and then some. Why do we need a metaphor for a human performance?
I think the reason why we today need a metaphor for that is that people or navigators today don't realize their important role in information processing. They see computers as information processors, and as I have tried to argue in the chapter that you are talking about, the most important sensor in this schematic is the navigator, as he or she is conducting information processing of all these sensors and the information is coming in.
Yeah, I think you just opened another door. Go to slide number 7. Yes, you're correct. You're entirely correct, but you didn't know this when you wrote this thesis. If you go to slide 7, the system. This is nice. We're trying to contextualize, because we have so many theories and models that are not contextualized. We have spatial task and system.
Sorry?
We have a spatial task and system awareness.
Yeah.
So what's missing? Given what you just told me.
Human awareness.
Self-awareness, teammate awareness, people. What is part of your system? Because you said, or the person who made the movie said, this is a team, they are communicating.
And I think we see it in two different ways, because I don't need, but I understand what you mean, but it's always been logical to me that the human factors of this it's kind of always on the side. The humans is always there, they will be there for a long time, and it's a bit funny that you mention it, because the slide that I did take out is a slide where the human factors is on a separate column, which we use a lot at the Navigation Competence Center, and it is extremely important.
But it's again, it's on the side. It's not. It's better than not being there at all, I guess.
Yeah, it's true. But to me, it's inherent. To me, it's. But I understand what you mean.
Yeah, because weekends, again, going back to the very first paragraph of your human performance, you say that this could lead to the assumption that the perfect design will allow the user to perform a task faster, etc. So, and you have a system. So I think part of the system is the person, or maybe even part of the task. But of course, going back to why we need a model or a metaphor for anything is you have to simplify.
But and also when I try to explain this model, I try to contextualize it for the humans in all the different, in spatial, in task, in systems. They are the inherent parts of all of the sub parts of the navigator's essay. But I see your point, and it's a lot more, of course, when it comes to teamwork and team resilience and communications and
Yeah, but then again, of course, your thesis isn't about teamwork.
No.
It's only about navigation training, attention, scan pattern, and design. So it sounds a lot when you put it like that.
Okay.
And I guess what your argument is that holding them all together is looking at can eye tracking be used for all of these. So in one way, it's a thesis about a technology trying to find a home for many uses.
But isn't that what we should do with? I feel that when starting this work, when sitting down with researchers and academics, I had a great fear of the knowledge for the other person sitting on the other table, on the other side of the table. And but then I realized that they had a fear for me, since I had contextual knowledge, since I knew how the vessel is operating, how thing actually works. And I feel that there is a gap between these two parts, and maybe that is kind of what you're saying, that I've been trying to bridge the gap between technology and something operational to be useful.
No, that's fine. That's like we can't do that enough.
Yeah.
Just like you say, we're seafarers are much too clever for their own good.
Yes. Or too stupid. Depends.
Yeah, because you could just say, I can't work with this system. But we don't. Seafarers don't, because it's professional pride to get it work, to sail to an export, to get it, fix it. It's fun. It's what makes it, or what made it seafaring was interesting, was get the ship to sail another trip. I was going to let go of this socio stuff in 1 second, because later in the thesis, surprisingly late, you talk about socio-technical systems. So if you talk about socio-technical, don't forget half of it. It doesn't seem to include many social
As a reflection, when I started the thesis, I tried to look at only technology, but I couldn't get rid of the humans.
Oh, how interesting! Maybe there would have been an artificial intelligence defending the thesis.
Maybe.
Did you want to jump in?
No, it's okay.
Connecting back to what you said, you were also in some planes, and quite correctly you say the research in aviation states that efficient scan patterns can improve situational awareness. How far can this comparison be drawn? And you've already started telling us about the difference between cockpits and bridges.
I would say that there is, of course, large differences between the maritime and aviation. Speed is, of course, one variable that is different, and we have in the maritime we have the possibility to stop. It's kind of difficult for a plane, or it's probably not difficult, but it's bad.
But they can go up and down. We don't like to do that.
That's true. But what I found, I actually thought that they were more into the scan pattern before I went on field trips in the cockpits, because what I then found is that they have different phases of the flight. They have phases where their attention level are much higher than other phases of the flight. For example, when they have come into transit and they're just transiting, for example, across the Atlantic, I would say that the attention level to me was kind of lower than I would have expected, while their attention level in critical phases of the flight, the departure and arrival phase, is extremely high. And that relates to the control strategy and the phases of navigation. In higher speeds, in demanding littoral waters, you have a lot of different legs all the time. So then you kind of are continuously in the departure and arrival phase. But you can't, as a human, you can't have the attention level high during a 6-hour watch, but it's seldom that you are in such waters for 6 hours, but say that you are, then you can't stay at that attention level for so long time. So I actually think that when looking at the demanding operations, I would say that compared to commercial aviation, I would say that it's very comparable. But of course there are differences, but the good things from both domains should be taken into account to provide something better.
Yeah, I met, just to connect again and to validate what you're saying, I met a Czech pilot from Qantas, and we were complaining about our respective workplaces, and he said, we have 2 different manufacturers. And I said, look, we've got like 60. And of course, like you say, the layout is standardized, I should say, but maybe not identical. But that still you can't move from one airplane to another without various checks, and we just let people move.
And if we took a raise of hands with this audience by the navigator that has gone on board a vessel and found a new system and just sailed, the ones not putting up their hands are lying.
Let's try it. Let's see how many. The moving towards the end, just a few words of quality of research. Would you say something about objectivity and insider research? Is it possible to do objective research? Is it necessary?
It's necessary. It's the objectivity is of course very important, and to be honest, when starting, one of the main reasons why I started the PhD journey was because I had experienced a lot of stuff during my operational career, and it annoyed me, and I wanted to fix it. And but as probably some of you that has discussed with navigators know, that if you ask 10 navigators, then you get 10 different answers to the same correct or to the same question. And what I have found important with the insider perspective is that it has given me insight into the context, and it has provided me with means to collect more valid data. And the good thing with the eye tracking is that as a quantitative data measurement is that it combined with the qualitative, combined with interviews, I would say that it strengthens the validity of the research, and also the use of the HCD process, when you also take in software engineers and human factor specialists, then you kind of have a bigger picture and you get more understanding of each other problems, which I think will provide for better solutions. And it's not rocket science, but it's not been very much done. But of course, there is always a chance that the work has been colored by my personal experience, and to say that it hasn't would. It has, of course, because it has been very important to me to further understand the context and to further exploit which areas I should dig into to get more data. And it has also, in many cases, I have been surprised. I have been expecting other data to validate my assumptions, but they haven't, because apparently I'm not perfect either. But,
self-awareness.
It's on the
It's
other side.
outside the box.
So
maybe objectivity is not necessary for an applied research of this.
if you to me, objectivity is not taking someone without context into that context and doing research. To me, objectivity is finding measurements that can produce, or using methods that can produce that can give objectivity to the research. I think that the research is strengthened by having a researcher that has knowledge into the domain. But maybe we look at the word, maybe I haven't read the definition of objectivity correctly.
I'm sorry, just no. I can pause. You can jump in.
When we start our exam, there was the poster on this table. Could you present the table? Yeah, exactly. And these figures are coming from the paper which was presented in the Transnav conference 2 years ago. But in your thesis, there is a little different explanation than in the paper. So could you explain once again what we can observe in this table? This is a recommendation or observation?
Yes. So when doing education in electronic navigation, one question that we see is often posted is, how much should I look at the different areas? The areas of importance is the outside, the electronic chart, the radar, and the conning application. And the question is kind of the same question as asking how large is a cod. It depends. But we wanted to provide a rule of thumb for how a navigator should think when it comes to the two main different conditions, which is good visibility, visual sailing mode, which is kind of compared to from aviation the visual flight rules (VFR), and conventional sailing mode, which is during low visibility, dense fog or similar. You don't have any visibility in front of the vessel, which can be compared to instrument flight routes (IFR) in aviation. So the important when you can see stuff is that you look outside. Mainly, you look outside to control that the vessel is safe, but of course in advance of this you have done a thorough planning process. You have your voyage plan, you know the details of it, and you can use some of the time to, because you have a limited working memory, you have to check. You have to check that you remember your plan, and we have the phases of navigation and the standard operating procedure, that where we collect information from the different applications to validate what we see outside the window. As an example, we collect information about turning point, heading mark, next course, next leg distance from the axis, and of course the dangers in the waters. But the passage plan sets you clear of the dangers in the waters, so that's kind of been done in advance, but you of course has to check on the way as well. The radar is very important as a terrestrial navigation mean, and it and also of course for collision avoidance. So it's used in both visual and non-visual sailing mode, but in non-visual sailing mode, the radar is the most important tool for the navigator. It's what makes him see through the fog. So that's kind of why it's flipped upside down. in the two different sailing boats. And as an example, with the conning information, and a very important phase is the turning phase. When you start turning the vessel, you have to collect the information from the instrument to see that the rudder actually gives the feedback that you have provided to it before you actually can feel it through kinesthesia, sense of movement. So you want to check that the rudder is in the correct position before you get the feeling in your body, the kinesthetic, the sense of movement. Because in some cases it could be too late when you get the feeling that it's going the wrong way.
Yeah, I start that you prepare some paper together with Professor Hareide. This paper you prepare with your supervisor, Professor Osnes. But could you explain what is the source of these figures? Is it any result of calculation, assessment, or it's your dream, or should be like this and finish?
When the first kind of eye-opener for us with the eye tracking data was that we got the measurements of how much a high-speed craft navigator looks out. And I had a pie diagram showing that 65% of the time it looks out, 20% in the actis, and 15% on 10% in the radar, and 5% on the rest. So that was kind of the start of this, and then we started to discuss with them what is taking your attention. Then we found some design issues which is taking much of their attention. As an example, with the 5% on other things, a lot of them were related to resetting the trip meter, because there is a button that you have to press, find. First you find it, then you have to press it, and you have to hold it for 2 seconds. And it's important that this procedure is conducted, so then you look at that display while conducting the procedure. So just by removing that time-stealing attention, then we could move more time into the outside. We also compared it to other eye tracking studies. One study conducted in Rotterdam with pilots, and pilots are, of course, very highly specialized navigators, and they have 90% of the time they look out the window. And then we discussed this with navigators, and I discussed it with my colleagues, and this was kind of a rule, the rule of thumb that we came to, which was something to strive towards.
So thank you very much.
Okay. I have one sort of interactive question and one last question. Remind me, you told me who were on the human-centered design team, or who should be on a human-centered design team?
Software engineers, end users, or firstly, end users, software engineers, and human factor specialists.
Okay, good. Why do you put human factors people in a group like that?
One of it's kind of very basic things that we tend to forget within ergonomics. The human factor specialist within the team, he constantly made us aware of the reach of the navigator, how the eye works, which colors are better to present in, that the fonts should be in this distance, 2.3 meters from a 26-inch screen. The size of the fonts should be this for readability, so that you don't see the movement like you did on the movie. You see the navigator always leaning back and forward to present as good as possible working environment for the navigator, which conducts a safety critical operation.
Could you go to slide 19? So I think you've made an experiment on us. So we have, is there any possibility that the difference in colors here could influence what we see? Does the dark color, I mean, look, is it, have you tricked
This
us?
looks better than this.
Well, the comparison, the purple looks smaller, but I'm wondering, does it look smaller because it's a darker color or it's another color?
We should ask a human factors session.
So, coming back to the human-centered design, you ask 10 people and you get 10 answers, or even worse, you get 12 answers, is what they say. I'm not going to accuse you, because it took me about 10 years to realize we were asking the wrong question. Because if you're not getting the answer you want, you're asking the wrong question from the wrong person. So that's my point. The human factors person is also there to translate between the engineer and the user, because you cannot directly ask a user what they need or what they want. Because a seafarer is not an interface designer or a bridge ergonomist. And an engineer is not a seafarer. But they don't understand each other. And the engineer wants immediately to know where do you want the information, what information do you want, how big do you want it, in which corner, what color, and then I'll go away and program it. And the human factors person is there to say, wait, you know, how far away is he going to sit? Is he going to do this in the night time? So the point is, we've been asking the wrong question for a long time, I think. And that's why we need the human-centered design. And to finalize this, imagine that we're 4 years from now, in the future. Dr. Odd is sitting in his office, and there's a knock on the door, and there's a young, fresh-faced PhD student saying, "Hey, you're my new supervisor." What are you going to tell them? The first thing you tell them? Run away.
Welcome into my office. Have a cup of coffee. Sit down, and this is going to take a long time.
Yeah. After we had the coffee, what's your best advice?
My best advice would be that he finds something in his project description that he is passionate about, and that he holds on to that passion throughout his work, and that he writes it on a note and picks it up every week and reads out that sentence to remind him of what he's actually doing.
What did your note say?
I didn't have one.
But you're still here, and I think your passion for technology and navigation, and maybe a little bit of people passion, got you this far, and I'm fine.
It's kind of, you hit me in a sore spot when you say this technology thing, because what I really think is important is the human. That you always put it the other way, but I know that you do it to annoy me. So
that's why I'm paid to annoy you.
Thank you, Professor Weintritt and Professor Margareta Lutzoft. There was no one from the audience that had questions or comments to the submitted thesis, so there will be no opposition ex auditorio. I think that is Latin for public. I have a question. That this is outside the defense. Excellent education and education programs have a close interplay with research. Asking good questions, continuous improvement, blending practice with experience, with science, and so on. A PhD work can be seen in this way. How will you make benefit of your research in your everyday activity at the Naval Academy?
I hope that journey has already started. As a technical manager in electronic navigation, I am I am lucky to be involved in processes both in operational vessels and with educations. And I would like to take this work to further emphasize the user-friendliness of the important support that you get from the digital systems. And I would also use the knowledge to try to explain to people that seafaring and navigation, we are not a dying breed, we will be there for a long time. Autonomy is kind of the word that many is using, but most have misunderstood. And that the role of the human navigator still is important for many years. The problem being, one of the problems can be that we need time, or we need people coming into the education that are motivated and have the right background and the right competencies. And we need time to form them to become the modern navigators that we need, and so that they can face the hard challenges that meet them when they come out into the real world.
You have put a lot of attention how it is optimal way to use your eyes, not only design but how to use the eyes. How are you teaching your students that, and how can you do that in the future?
Here at the Naval Academy we are lucky to have a course called Military Practical Navigation, and we have a sailing vessel and the simulators where we constantly practice the use of the eyes. And it has partly been implemented, but it needs further work to make the navigators understand the importance of the work that they are doing and give them the tools to better do that job, which maybe the maritime scan could be one of those tools.
I'm slightly jealous on your stripes. Will you have one more stripe now?
You have to ask the commander for that.
You just give them away. At university, when we are promoted, we just get more work. No stripes. Okay. On behalf of the National Joint PhD Program in Nautical Operations and the Norwegian University of Science and Technology, I thank the committee for their work. I hereby declare that these proceedings are concluded. A report will be made to the program board for the National Joint PhD Program in Nautical Operations. I will read from the report for you, but it is the board that decide finally if you can start using the term PhD. At last, I want to thank you all for participating in this defense.
Thank you so much, Chairman. Sveinung, we are impressed by the endeavor you have done here. So on behalf of the Royal Norwegian Naval Academy family, with academics and with operations and the admirals on the top, here is a little token of appreciation for this endeavor. So fair winds and following seas.
Thank you.